Okay, so let's get started. First, I want to just acknowledge that everything I'm talking about today has been worked on with others. And so I just want to give a quick acknowledgement to those who have worked with me in the past at ASU, Professors Colburn and Montgomery, at Virginia Tech, Laura Freeman and Adam Edwards, Old Dominion, Sachin Shetty and Saeed Ahmed, at University of Virginia, Peter Beeling, Tyler Cody, and Stephen Adams, at NIST, Rick Kuhn and Raghu Kakkar, and at MITRE, Eric Blodern. Okay, so what I'm hoping to cover in this tutorial today is we're going to talk about combinatorial interaction testing, and we're going to talk about how it fits into software testing, the basic ideas of combinatorial interaction testing, which I'm just going to call CHIT from now on, how combinatorial arrays are used as CHIT test suites, some methods of constructing combinatorial arrays, what you can do if you don't want to write code and work on algorithms that construct arrays, how you can still use them for testing. And then some ongoing research that's really, we're just getting started in this area. So a lot of it's just in progress, but how we can use CHIT metrics and apply that to testing within the machine learning domain. So first, let's just do a brief intro of software testing. So I don't think I need to explain to this group why we should do testing, but just in case there's anyone who still doesn't think it's important, why we should test software and systems. At best, they can cause annoyance. So there was a 2005 World of Warcraft contaminated blood virtual pandemic that killed off characters. In the average case, they result in financial or privacy loss. And there are many, many instances of those. OPM breach that revealed background information or target credit card numbers were stolen, losses were about 162 million. And then they can also cause death. There were these two instances of bugs in radiation devices that ended up delivering doses that were much higher than should have been delivered and killed quite a few people. So where does testing fit within the software development lifecycle? We know, most of us know about verification versus validation, or V&V. Validation is checking whether or not the specification meets the client need. So did we build the right system? Whereas verification is checking whether the software meets the specification. So did we build the system right? And then we have levels of tests. So what are we testing at each level? When we're testing at the unit level, we're looking whether or not a block of code achieves the function that it's intended to achieve. At the integration level, we're checking that communication between functions that are collected into a module, or those interfaces between modules, work correctly. At the system level, do the composed modules and the environmental conditions, do the composed modules work inside the environmental conditions with the overall behavior of the system? At the acceptance level, does the system meet the user needs of the customers or the operators? And then in regression testing, we're checking that changes to the system did not impact the prior functionality. In other words, nothing broke when we were trying to add new functionality or fix some bug that has been identified. In this talk, I'm going to be focusing on the things that have been highlighted in orange. So I'm focusing on verification testing and integration testing. We also have Blackbox and Whitebox testing paradigms. So Whitebox is testing where we have full knowledge of the system. And so tests are derived from the system internals. We can examine the source code directly. But this tends to be expensive and time consuming. Its goal is to be exhaustive. We're typically doing this when we're doing, say, unit testing, looking at the lowest level. In comparison, we can also conduct black box testing, where we have no knowledge of the system or little knowledge of the system. Tests are derived from external descriptions, such as from the specification. We're asking the question, given some input into this black box, what is the output? And exhaustive is typically not possible. We have the question, how do you know when you've tested enough? In this talk, I'm focusing on black box testing. How do we know where we've tested enough? We have this notion of coverage criteria. So both white and black box techniques can use coverage criteria to determine whether the testing was sufficient. So Whitebox techniques include structural code coverage. So has every statement in the code been tested? Has every condition? So if I have like true and false, or if A is less than B, then I want to check that every time I've seen a situation like if A less than B, then that I'm evaluating both A less than B is true and A less than B is false. That would be checking all conditions. Are all paths through the code covered? So when we have branching statements, do I take one branch in a test? Do I take another branch in a test? When we're doing black box testing, these techniques include coverage of the input space. So performing equivalence partitioning. So if I have behavior that's expected to be the same for all individuals less than the age of 18, and then maybe behavior from 18 to 36, another behavior from 36 to 65, and then 65 plus. In that case, we're going to split the inputs into equivalence classes and then select an example from each class. Boundary value analysis, checking at the boundaries. So I would check for that case I just explained. Maybe a value 17, 18, and 19 covers the boundaries around those two equivalence classes. And then also combinatorial techniques, which is going to be the focus of this talk. So given a set of values to be tested, a test that includes that value is said to cover it. And coverage gives us a measurement of test set quality. Each test has a cost, so we would prefer a minimal set that also provides coverage. So if we assume that the values to be tested are just abstractly A, B, and C, a test set that has A, B, and A would cover 2/3 of the criteria. A test set that covers A, B, A, C, or a test set that includes A, B, A, C covers all of the criteria, but it includes redundant tests. So the test set A, B, C covers all of the criteria and it's also minimal. Okay, so jumping into basics of combinatorial interaction testing, or CHIT. When we have software faults, they can be caused not just by errors in single components, but interactions among multiple components. So that's the case that all levels of component A and all levels of component B work just fine independently. But when we have component A configured to some level, let's say I, and B configured to some level, say J, we suddenly get a fault. So we can think of it as we have a system under test that has 3 operating systems. It has 2, let's say, printer drivers and 6 browsers. And then if we're running a test suite and we have the case that when we have Windows and Firefox and printer driver 1, it passes, but Windows and Chrome and that same printer driver, it fails. And maybe there are some tests that we can't run. Maybe we can't run Windows with Safari. And so if we just run a test suite that hasn't been created to check for faulty interactions, we might not be able to figure out which interactions are actually faulty. And in this case, I designed the passes and fails around the idea that there was a fault in Chrome and printer driver 1. And so when we design a test suite that includes coverage of interactions, we're able to find these fault-inducing interactions. CHIT is a black box, pseudo-exhaustive testing method for integration testing. So often testing all of the interactions is infeasible for large systems. So if I have K components, and let's just say each of my component has V values, then I need to run V to the K tests if I want to test every possible case. So that'd be a full factorial. However, in a survey, it was found that nearly all faults are caused by interactions of limited size. So typically covering somewhere between 4 to 6 of the interactions, of size of interactions, found all of the faults. So if we look at the at the chart that's provided, these are different systems. And then the number of parameters or the number of components that are involved in the faults is along the bottom. So we can see that if we only test one component at a time for the systems, somewhere between 18% and let's say 68% of the faults were found. When we allow testing up to interactions of size 2, that jumps to about 62% of the faults to 97% of the faults are found. At around 4, so when we're looking at interactions of size 4, close to 100% of the faults are found. And by the time they increase the size of interaction to 6, effectively all of the faults were found in the systems that were being checked. So what this means is that for these systems, at least, it wasn't necessary to check interactions of, say, size 7 or 8 or 9 because all of the faults in the systems were found. This doesn't mean that there isn't a system that doesn't have a fault that's caused by a 7-weight interaction. It just means that in the software tested in the survey, most faults had limited size, somewhere between 4 and 6. And so we can think of doing pseudo-exhaustive testing to give us some assurance that we have found most, if not all, of the faults in software systems. We can think about framing this as a T restriction problem. So if we test all of the T-weight interactions for each of the K-choose-T combinations of components, this would cover each T-way interaction in the system. And again, T here, let's say 4, we're looking at 4 components at a time. So CHIP provides pseudo-exhaustive testing of interactions, and it's structured by combinations of components. Okay, so some terminology. Factors are atomic units in the system under test. So in this example, my factors are operating system, printer driver, and browser. So I'm not thinking about testing a line of code within the operating system at this level. I'm testing the operating system as a whole. It's not decomposable at the system under test that we're considering here for integration. Other terms used for factors are components, inputs, parameters, or variables. Depending on the paper or the group that's discussing it, they might use any of these terms, and they all mean the same term that I've defined as factors. We use the variable K to discuss the number of factors in the system under test, typically. Factor levels. Each factor has a finite set of levels it can take on in a test. So again, in this example, the factor levels for the operating system are Mac, Windows, and Linux. The factor levels for the browser are Internet Explorer, Chrome, Opera, Firefox, Safari, etc. Other terms that are used, some people use the term values and some people use the term settings. Continuous valued factors have to be discretized in order to apply combinatorial interaction testing. When all factors have the same number of values, we say that it is fixed level, and we use the variable v. When we have the mixed level case, we have different number of values or factors or levels for a factor. Then we use v sub I to mean the number of values or levels for factor I. And then a T-way interaction. We know that multiple components at certain levels can interact to cause a failure. So a T-way interaction is an assignment of specific levels to T factors. T is the size of the interaction, so it's the number of factors being considered at a time. And another word used for T is the strength. Other terms used for T-way interaction are just interaction, value combination, because we take a combination of factors and we assign values to them, variable value configuration or configuration. You can imagine that when we're saying it's a system that is running a Windows operating system and it has a Chrome browser, that's a configuration of the system. So some related combinatorial techniques. All of the combinatorial methods are going to test combinations of inputs. Each choice technique tests all values for each input. It's equivalent to T-way interaction testing where T is equal to 1. So for every way to assign a level to one component, there is some test that covers it. So in the examples to the right, I'm assuming I have 3 components or 3 factors. And each of those factors has 2 levels, 0 and 1. And so the top array would be a test suite where I'm testing each level or each choice for each of the factors. So again, factor 1 gets seen at level 0 and 1, factor 2 at 0, 1, and factor 3 at 0 and 1. Base choice is a test to change the value of each input while keeping the others constant at the default or base value. It's equivalent to testing T-way interaction, testing with T equals 1, but it also covers more than just that. But it may not cover T is 2. So the example to the right of base choice, the assumption here, again, I have the same number of components. Each component appears at 2 levels. And we're assuming that the default level is 0. So here we keep the other factors at 0 while we change, you can think of like the targeted factor to its other level of 1. And if there were additional levels, say 2 or 3, then we would have tests that would have all the other components or factors set at level 0, and then you would see a 2 in 1 column for that row. And then you would see a 3 in 1 column for that row. So in this case, we're seeing that component 1 gets tested at level 1 in test 2, component 2 gets tested at level 1 at test 3, etc. And then all pairs testing tests all pairs of combinations. So it's equivalent to T-way interaction testing when T is 2. So here, again, same number of components, same number of levels, and then we would just check that we would see 0, 0, 0, 1, 1, 0, and 1, 1 for each pair of combinations. So that's really easy to see for the pair C1 and C2. If we look at C1 and C3, they go in a slightly different order. They go 0, 0, 0, 1, 1, 1, 1, 0. And then it's also fairly easy to check for C2 and C3. For combinatorial interaction testing or just combinatorial testing, most often we're referring to just the general T-way interaction testing. Okay, so let's talk about some combinatorial arrays. How do we test with common combinatorial arrays? First thing that we need to do is define the system under test. So again, using the variables that I've defined before, let's say that a system has k factors and it has VI levels for the ith factor. We need to discretize continuous leveled factors. And then either determine the expected size of T given similar systems or some subject matter expert knowledge of expected interactions, or determine the number of tests that are affordable and then maximize the size of T that we can get given the number of tests that we can run. And then we can represent our test suite as a combinatorial array. So it's an n by k matrix or array where each column represents one of the k factors in the system. And each row represents one of the n tests in our test suite. Different arrays have different properties over columns and rows. I'm really going to talk about covering arrays and locating arrays and give a brief mention to detecting arrays. So a covering array is an n by k array on V symbols where every T-way interaction appears in some row. So the notation we use is CA for covering array, and then we give the number of rows in the array, and then we give the parameters T for the strength, K for the number of components, and V for the symbols. And we have fixed level factors. When we have mixed level factors, we use MCA, and again, we list N is the number of rows in the array, T is the strength. And then we list out each of the levels for each of the factors. So V1 would be the number of symbols that we would see in column 1 for component or factor 1, all the way to VK would be the number of symbols that would exist in the kth column representing the kth component or kth factor. And then we have a different notation when there are J columns that all have VI symbols. So we have VI raised to the J exponent. So if there are, let's say, 3 columns, 3 components that all have 2 levels, then we would just write 2 to the 3. And then we would have the next one. Let's say we also had 3 other components that have 4 levels, then we would write 4 to the 3. What does a covering array do? It provides coverage. So it ensures that all T-way interactions for the specified value of T occur in some test in the test suite. This means that if a fault exists that has strength up to T, it will be discovered in some test. When we run the test on deterministic software, then that faulty interaction will cause a failure. And so we would report on that test that this test failed. How does it fail? Maybe it crashes, or maybe it does not give us the same output we were expecting. So we have some test oracle that says, when I put in length times width, then I get area. And if I have certain values for length and width, I get a different area that's reported. So then we would mark that test as failing. How do we verify a covering array? Pick any of the T components in the system, then list all interactions of levels of the T components. Look in the array at those T columns, and then just check off. Some row must have the symbols for those levels. So we can go through. I verbally went through, oops, you know what, I'll just go ahead. We'll go forward and I'll end up checking them. Okay, here we are. Okay, so this is a fixed level covering array example. It's a covering array with 12 rows. It has strength 3, so T is 3. We're looking at interactions of size 3. It has 5 columns, and each of the columns has 2 symbols in it. So it has 2 levels for each of the factors. This one was created in JUMP. And then if we wanted to manually verify that this is indeed a covering array, maybe we have some test suite that wasn't designed to be a covering array and we want to ask whether or not it is, how would we go through and verify? We would need to look at each of the K choose T combinations of columns. K is 5 here, T is 3. So of all of the 5 columns, we're going to pick out 3 at a time and check them. In this case, I'm showing the verification for columns 1, 2, and 4. And so since we have 3 components to check, and each component has 2 levels, then we have 2 to the 3 combinations that we need to find, or interactions that we need to find. And so we can go through them one at a time. We're looking for 0, 0, 0, it's in row 2. Looking for 0, 0, 1, it's in row 3. 0, 1, 0 is in row 4. 0, 1, 1 is in row 7. 1, 0, 0 is in row 9. 1, 0, 1 is in row 8. 1, 1, 0 is in row 6. And 1, 1, 1 is in row 1. A locating array is an n by k array on V symbols where every T-way interaction appears in some row. And additionally, every set of D of the T-way interactions appears in a unique set of rows. We use the notation LA, ND, TKV when we have fixed level notation. Again, this is N is the number of rows, D is this set size of T-way interactions that we're going to consider. T again is the strength, K is the number of components or factors, or the number of columns in the array, and V is the number of symbols. Notation for mixed level is similar to what we did for covering arrays. And there are variations on locating arrays that instead of being exactly D and exactly T, go up to at most D or at most T, meaning if I have a set of no more than D T-way interactions, or if faults are caused by interacting components of up to size T. We have variations of locating arrays for those cases. Locating arrays provide fault location. So if system faults are caused by T-way interactions, and if there are D faults in the system, the faulty interactions can be uniquely identified by the set of rows in which the failing tests are recorded. So something important to note is that with covering arrays, we don't have this additional property of location. So that might be the case. Let me go back to my covering array example. I don't know if I have one here that I can point to right away. But let's say that everywhere we see 0, 0, 0 in columns 1, 2, and 4, everywhere we see that interaction, we also saw a different interaction. Let's say that that was the case. And let's say that those are the set of rows that are failing. It is not possible then to be able to say which interaction is causing the fault. We know that one of the interactions involved in that test is faulty, but we don't know which. There are methods that can be applied adaptively after the fact to dial down and run additional tests and try to figure out which one is causing the failure. But when we have a locating array and we have defaults in the system, then we can uniquely identify the interactions that are causing the fault. They're not masked by others, or I should say obscured by other faulty interactions. How do we verify a locating array? We pick, again, any T of the components in the system. We list all of the interactions of levels for those T components, look in the array at those T columns. Some row must have the symbols for those levels. So that part's similar to covering arrays. This is the part that's different. We're going to form sets of D of the interactions. So if D is 2, then take interactions, and for any way to pick 2 of the interactions, that's going to be a set. We're going to look in the array and list the rows in which each of the sets appear. So if I'm looking at every way to form sets of 2 interactions, then I've got my list of interactions, and then I write out all pairs of interactions, and then I write out all of the rows for each of the pairs. And then no 2 sets of rows should be identical. So let's go through an example. This is a mixed level locating array on 2 symbols with 3 columns and 10 rows, and it has strength 2. Okay, so we see there's 10 rows. Again, there's 3 columns, and each column has 2 symbols in it. Oh, actually, I wrote that wrong. Okay, the first 2 columns have 2 symbols. So we see in the second set of parentheses, the inside parentheses, the first component has 2 symbols, the second component has 2 symbols, and the third component has 3 symbols. And this is 1-2 locating. So if we look at the rows for the 2-way interactions, the second table, we are looking at taking 2 of the components and listing their interactions. So if I look at C1 and C2, that's the first and second column. If I look at the symbols, so 0, 0, what I mean there is that symbol 0 appears in column 1 and symbol 0 appears in column 2. Those occur in rows 2 and 8, and you can verify that. Likewise, if I went to look at where column 1 has symbol 1 and column 2 has symbol 0, so I'm looking at the 1, 0 row, then that would occur in rows 3, 5, and 7. And in this way, we write out all of the interactions and all of the rows in which those interactions occur. And again, this slide is a little bit wonky, so I messed up some of my numbers on this slide. This one is 1, 2 locating. So D is 1, T is 2. For each set of 1 two-way interaction, the set of rows for that one two-way interaction is unique. So if you look through the table, these are the sets of rows in which the two-way interactions appear, and none of the interactions, none of the values in a cell is the same for any other cell. So I have a 2 and an 8, and I can look through the table, and nowhere else does a 2 and an 8 exist. Now, this same MLA is not 2-2 locating, and it's not 2-2 locating because there are ways to form sets of two-way interactions that have the same set of rows. So if I look at the interaction C1 at 0, C2 at 0, it has rows 2 and 8. And if I form a set using that interaction with the interaction C2 at 0 and C3 at 0, that interaction occurs in rows 2 and 7. So then the set of rows for those two interactions taken together would be 2, 7, and 8. And then we can look down and see that if I also form a set of two-way interactions using C1 at 0, C2 at 0, and C1 at 1, C3 at 0, I also form the set of rows 2, 7, and 8. So if I use this MLA as a test suite, and the set of rows that fail are 2, 7, and 8, I can't tell if that was caused by the interactions highlighted in the top right table, or if it's caused by the interactions highlighted in the bottom right table. So this fails to be 2-2 locating, although it is 1-2 locating. Okay. So what are some other concerns that we might have? We might have constraints in our system. Some combinations might be dangerous, they might be impossible, they might be untestable, or they might not be required. So like a dangerous scenario, if this is not software, but it's some kind of mixture experiment and you have two chemicals that you're putting together, two chemicals put together might explode your plant. So that would be a dangerous combination. You would not want to test it. An impossible scenario might be one where we want to run Internet Explorer on the Mac operating system. If that piece of software, that component doesn't exist in the presence of the other one, then it's an impossible combination. Constraints can also just be not required. In that sense, they might be a don't care constraint. And so there are different kinds of constraints as well. I'm not going to go in too much depth into that, but we can have constraints that we forbid to appear, and then we can have constraints that we just don't care if they're covered. We can also be concerned with variable strength. So some interactions might be more important, and they might be required to be tested at a higher strength than others. So we might want to test certain components in four-way interactions, where other components, we only care about seeing them in pairs with other components. We might require that some tests have to be run first. So if we have a scenario where we have a full test suite, but we might run out of time, we might want to make sure that the tests that are most important occur early in our test suite. Or there might be tests that the full combination, the full configuration, some values assigned to every one of the components, that those really need to be run. And so we'll concede our combinatorial array with those tests and then just fill in the rest of the tests to achieve coverage. And then last, I said I'd mentioned detecting arrays. They are like locating arrays, but they're more powerful. And they require that sets of rows also not be subsets of other sets. So this prevents masking. Next, let's talk about combinatorial array construction. So let's say that you've decided, great, we would like to do combinatorial interaction testing. How do we get a combinatorial array to use? Constructing optimal combinatorial arrays is challenging. Covering arrays are well studied, and there are many approaches, but no method produces one that has the fewest rows in the general case. So the best known arrays in the literature are reported at this website. And different approaches produce the best array depending on the parameters tk and v. So at the right is a chart from the page when t is 3 and v is 7. And so when the number of components 8 is 8, then using an orthogonal array produces an array, a covering array with the fewest number of rows, and that number of rows is 343. And as you can see, depending on which K we are interested in, the method, the algorithm for producing the best reported array changes. So it can be very complicated to decide what should we use if we are really, really concerned about minimizing the number of tests. If minimizing the number of tests is the most important thing, then probably consult these tables and figure out which algorithm would be best to use. If minimizing the number of tests to this degree is not that important, then there are some tools that we will briefly cover that you can use. Locating and detecting arrays are still largely unexplored. Many of the techniques that work for covering arrays can be adapted to locating and detecting arrays, but many cannot. So what are some of the construction approaches for covering arrays? They generally fall into two different classes. There's the mathematical constructions and the computational constructions. Mathematical constructions use features of an underlying algebra. They usually work for restricted cases. So a mathematical construction might only work for fixed levels. They might also only work when levels are a prime power or a prime number or some other specific case. They tend to produce better arrays that have fewer rows, and they are usually quite fast. They can be compared, mathematical constructions can be compared against each other as either direct constructions that make the entire array at once, or recursive constructions that build an array from smaller ingredients. Conversely, computational constructions often work in more general cases, so there are fewer restrictions for most of the computational constructions. They often find solutions that have more rows than the mathematical constructions. They also might be slow. Depending on the construction that you're using, it might be faster than other constructions. And often there's a trade-off between speed and the fewness of rows. So things that are very fast might produce more rows, and things that are slower and require more computation. Did I say that correctly? Things that are very fast produce more rows, and things that require more computation tend to produce fewer rows. They typically work better in the presence of constraints, and many of them are generalizable to mixed levels. They can be compared against each other as building through some intermediate arrays, like a post-optimization approach. We'll take a candidate array and then do some optimization on the candidate in order to reduce it to a smaller and smaller array. Or they work one piece at a time. So they either build an array one row at a time, or they build an array one column at a time. Some are deterministic methods that always produce the same result, and some are non-deterministic methods. Some are greedy, and some are using heuristic search. CATS is one computational construction. It examines the list of possible test cases and chooses the one that covers the most uncovered interactions. It's impractical in situations where the number of possible test cases is too large to fully store or examine, but it provides guarantees because it always picks the best choice. ATEAGE is non-deterministic. It builds one row at a time, and it's a greedy algorithm. Candidate rows are generated by looking at which factor and level most frequently appears in the list of uncovered interactions, and then it produces a random ordering on the rest of the factors. It chooses an assignment of levels to the factors that covers the most, depending on the partial row already constructed. And then after a certain number of candidates have been created, it chooses the best one and repeats until the uncovered list is empty. So many of these computational constructions start off by enumerating all of the interactions that have to be covered. And then as it goes through and builds rows, it effectively checks off those interactions that have appeared in some row as having been covered, and then iterates through until the uncovered list is empty. IPO, or in-parameter order, begins by building a covering array for T columns, and then it builds one column at a time in 2 phases. The horizontal growth phase chooses a value for each row of the new column that covers the most uncovered interactions involving that column. And then if there are interactions involving the new column that are not covered in the existing number of rows, a vertical growth phase adds rows until all interactions are covered. And so this one builds up through intermediate arrays that adds one column at a time, and each intermediate array is also a covering array. So let's say you wanted to build 10 columns, you will have 10 components in your system. Then by the time you have added 5 of the components, you have a covering array on 5 components. And then once you add the 6th column, you have a covering array on 6 components. Versus the one row at a time algorithms like ATeach start out with all 10, let's say, columns at a time, and builds up by rows. And so in an intermediate time in the algorithm, you are not guaranteed to have a covering array. You might have 50 rows and 10 columns, and it's still not a covering array. And it might not be a covering array for the first 5 columns. So that's the difference between those that build up one row at a time and those that build up one column at a time, or at least this algorithm builds one column at a time. Heuristic search is a class of algorithms that can be used for computational constructions. They generate a set of rows, usually randomly, and then they evolve the candidate by applying some meta heuristic that determines the fitness of a given direction or set of candidates, usually in terms of how many newly covered interactions are affected. And then it repeats until all interactions are covered. Performance frequently is dependent upon tuning of parameters, and this can vary depending on the type of instance. It often performs better than greedy approaches, as there are kind of opportunities to continue to manipulate an array once you've started to build it, but it tends to require more computation. With greedy approaches, once we've made a decision, we have built a row. In general, we do not go back and change that row, versus heuristic search allows us to change rows that we've already created. Some of these techniques include hill climbing, great flood, taboo search, particle swarm, ant colony, genetic algorithms, and simulated annealing. And so the meta heuristic there is, how are we going to decide to keep looking effectively? And then 2 last computational constructions. Random chooses rows from a set of possible test suites at random, and it does so until all interactions are covered. You can imagine that this tends to not be very good. Random selection tends to not work well, but it requires really no computation at all. It just requires keeping track of your uncovered list, and each time you have generated a new row, checking off what is still to be covered. As such, it's useful for comparing other methods against. One way that it's less useful is that one run of the random algorithm could produce an extremely different array than another run of the random algorithm. So if you wanted to really compare against the random algorithm as a method, you need to do many runs of the algorithm, produce many arrays, and then take averages. Anti-random or adaptive random is based on the idea that rows should be as different as possible, and it uses a distance measure, such as Hamming distance, to compare rows. So it chooses a new row so that it's furthest from every row chosen so far, or so that the total distance of all rows is maximized. So the idea here is, you can imagine that if I have a row, let's go back to an example that I can talk through. Here we go. So let's say that I started off with row 11010, and that covers so many interactions in it. If we're looking at three-way interactions, if I make the next row to be 11011, you can imagine that it does not cover as many interactions as a row that might be different, quite different. So that's the idea behind random and behind anti-random. Okay. So perhaps you've decided that you are not as interested in combinatorial array algorithms as I am. This is not what you find to be fun. And you would rather just have a tool that produces test suites for you so that you don't have to write your own code. Luckily, there are two tools that do that. I am not an expert in either one of these tools because I really like writing algorithms to find combinatorial arrays. But I've walked through the tools enough to be able to generate some examples. So the first tool that you can use is JUMP. It's probably familiar to those who already do design of experiments or statisticians. So in JUMP, what you do is you go to the DOE tab at the top and you scroll down to the special purpose menu item and then scroll over to covering array. And it gives you the little tooltip that you use a covering array to test combinations of features. And then when we open the dialog, for the covering array to build up, it gives you the options to add a factor, to add end factors, and to change the strength. So as we walk through and we add factors, we can add factors that have different levels. When you click on I wonder if I can walk us through this. I think I can. Just have to move my screens around a little bit. Can I? Sorry, Zoom, the way Zoom manages having multiple screens at a time is just a little bit challenging for me. Okay, so yes. Okay, I want to select multiple windows. Let's see. Okay. Hold shift to select multiple windows. I also want to do desktop 3. Maybe not. Okay, well, let's just try. I will just switch to this desktop and share that one, and then we'll come back. Let's see if that worked. Okay. Okay, so are you seeing my my desktop now has the JUMP window? Great. Okay, so we go into DOE and special purpose and covering array. And if I click there, we went to a different window, of course, we would be in the DOE covering array dialog. So as I click on add a factor, I can choose the levels for my factor. And so in this case, we could choose a 2-level factor. We could choose a 3-level factor to add, and let's add another 2-level factor. So I'm not going to go through writing all of this again because I don't type particularly well under pressure, but I will bring up the dialog where I created the example. Hopefully you see all my windows. And so here I've added an operating system named factor that's categorical, and it has Mac and Windows values. I also have a browser. It had 3 levels, so Safari, Chrome, and Internet Explorer, and a printer factor that had values HP and Canon. And then if we want to go to adding constraints, we can use disallowed combinations. And then when we use the filter, we want to go through and say that we are not going to allow using Mac operating system and Internet Explorer. So we click on operating system, and add, and I'm going to click on Mac. And then I'm going to say, I'm not going to allow Mac and browser, Internet Explorer. And that's one of my constraints. And then another constraint is I'm not going to allow operating system to be Windows and browser to be Safari. Okay, and so hopefully I have I've clicked everything that I need to click, and then I click Make Design. And so here you see that I have my design, and it has Mac appearing with Chrome, Mac appearing with Safari, but Mac never appears with Internet Explorer, so that worked. And then I have Windows appearing with Internet Explorer and Windows appearing with Chrome, but Windows never appears with Safari, so that worked. So I've checked the two-way interactions. Oh, I forgot to mention that I was setting strength to be 2 up here. And then we could also check that I see Mac with Canon and Mac with HP. And then I see Windows with HP and Windows with Canon. So those are all there. And then I need to check for the 6 interactions between browser and printer. So I see Chrome with Canon, Chrome with HP, Internet Explorer with Canon, Internet Explorer with HP, Safari with HP, Safari with Canon. So they're all there. And so now I have number of runs is 6. So I have 6 tests in my test suite. I have 100% coverage of my two-way interactions. And it's also giving me some information about the next level up. I've got 75% coverage of the 3-way interactions. And so then if I was ready to use this, I could make table. And then it's going to give me the same table that I had created over here. Okay, so that's using jump to create a covering array. And I sent out, I believe they've posted, I sent out this script that creates this if you want to play with it. So that's there. And then the other one that maybe I can do live, hopefully we'll see, is using the ACTS software. We're going to run through the same example. Maybe. Let's see if I can do it. Okay. So to use the software, we go System to New. And in fact, so here we would enter a system name. We would give the parameter names. I tend to use enum, which allows me to list out the values that I want to add. And then I would give the value and click the button add. And once I have all of my values, I would add them to my table. And then on the constraint screen, we can enter our constraints in the constraint editor and then add them. And then once all of this is done, we can add these to the system. Rather than typing that in, I'm going to open my example maybe. There we go. Okay, so here we can see I had used those dialogues. Let's see if I can do that. Edit, modify. Here we go. So here's that same dialogue, and you can see I've added the parameter names, operating system as an enum, and I've given the values, browser and printer. And then in the constraints tab, how I've written these constraints is that if the operating system is Mac, then the browser cannot be Internet Explorer. And if the operating system is Windows, the browser cannot be Safari. I'm going to not modify the system because I didn't actually change anything. And so then you would see the systems specified here. And then in my operations, I can go to build. And then I can select the algorithm. We have the in parameter order algorithm that it's using. Using forbidden tuples for constraint handling, strength is 2, building from scratch versus extending. If you had a set of prioritized tests that you wanted to run, you can provide those as a seed and it'll build from those. So if you have a partial array that you want to start from or a partial test suite. And then we can click the build button and that's okay. I'm going to say okay to that. And then here is my test suite. So again, we could check it again. I should see Mac with Safari and Mac with Chrome, and I do, Safari and Chrome. Windows appears with Chrome and Internet Explorer, but Windows never appears with Safari, and Mac never appears with Internet Explorer. And then we could also go through and check. I see Mac and Canon, Mac and HP, Windows and Canon, Windows and HP. And then I see Safari with Canon, Safari with HP. I see Chrome with HP, Chrome with Canon. And I see Internet Explorer with HP and Internet Explorer with Canon. And so then so we have our test suite using ACTS. So I'm going to go back to my slides, hopefully. Let's see. This one, share. Okay. And then, let's see. Do you see my PowerPoint slides again?
I see ACTS.
Ah, okay. So no, I did not do that. Oh. Share. How about now? Do we see? I'll go back. Do we see tool
Yes.
demo?
Yep, you're good.
Okay, fantastic. Okay. All right. So again, in the slides that have been shared, there's screenshots of walking through these two different tools. In both of these situations, these are extremely simplistic examples that I've encoded, because anything more complicated than this probably would not have been completable in the time that we have. But both sets of software have really good user guides that I recommend checking out. And so hopefully
we have just one question in the chat. It's asking, is ACTS a free software? I think a Combinatorial either requires Jump Pro or the latest version. Is that something you know the answer to?
I'm sorry, I didn't catch that question.
If you look in the chat, you can see the question is asking if ACTS is free software, and then there's some other questions about Jump.
Okay, let me pull up my chat screen.
Well, they're answering their own questions.
Okay, so ACTS is free software. Yes, it is distributed by NIST. You just have to email them and ask. Basically, you just have to email them, and it's available for download. Great, thank you, Rick. And so there is a link in the chat window to the ACTS software. Okay, and that I did not know that covering arrays were Jump Pro only. That's the only version of Jump I've ever had. So good to know. I think that my suspicion is that the two different software packages are useful for slightly different needs. The Jump software is really, really great if you want to go and analyze the results from your experiment. I also think that if you already know how to use Jump, using the covering array generation is pretty easy in Jump, if you already know how to use Jump. That said, I think that the ACTS software has a lot more functionality for combinatorial testing. So if that's really what you need, then that would be the software that I would learn how to use. And if it's really just a slight extension to design of experiment statistical software, I would look into Jump first. I'm not intending to sway anyone either direction, but just saying these are two different pieces of software that are available, that are both useful and both serve slightly different purposes. Okay. Okay, so now in the last half hour that I have, I would like to talk about, so hopefully what I'm hoping I have covered so far for everyone is what's a quick overview of software testing. Why do we need to be concerned with interactions among software components? How can we test for interactions among software components using combinatorial interaction testing? what are some basic terms that are used, and knowing that these terms vary depending on which subgroup in the community you're talking to. So I've tried to give a lot of different terms that a lot of different terms for the same concept so that you can kind of change your lingo depending on who you're talking to. I've hopefully explained some of the foundational ideas behind using combinatorial arrays for combinatorial interaction testing, some of the ways that we can build combinatorial arrays, and some of the ways that you can get your own covering arrays if you don't want to learn how to write combinatorial array construction algorithms. So that's what I've hopefully achieved in 60 minutes. And I'm happy to take questions by email after, or if we have any time at the end, I'm happy to take questions, but I just tried to jam a bunch of information at you. So hopefully that was successful, and hopefully you've learned something useful that you can take moving forward. And so in the last 30 minutes that I have, I would like to talk about some of the new work that we have been exploring to try to apply combinatorial testing for machine learning. So that's what I would like to do in the next, I guess I have 27 minutes. Okay, so testing systems with embedded machine learning is important. I'm going to focus on the situation where we have some classifier model, and the model has been trained on examples that consist of values that have been assigned to features and also have a class label. So that's the general concept behind a classifier model. The task is to correctly predict the label for an example that was not seen in the training set. When classifiers are built on big data with high dimensionality, they tend to have complicated structures. So they might have it might be a deep neural network. It has many layers in it. Each layer has many nodes, and these nodes are activation functions and weights, etc. And so the full network can be very difficult to examine, and it can lack explainability for its decisions. It might not be possible to look inside the network and say, aha, I see that this image is being classified as a wolf and not a husky because these weights are set this way. Additionally, machine learning is subject to bias. The machine learning models learn from the examples that are provided when training the models. And so if the examples that have been provided are biased, then the models will be biased. So, some examples are if the only images that have been provided to the algorithm are those of adult men, then the classifier might not do well in detecting pictures of adult women. Or it might not do well if all of the images that have been provided that include snow are images of wolves, and images that of huskies do not include snow. So a seemingly accurate wolf versus husky classifier in the link at the bottom was found to be actually learning to detect snow. So testing systems with embedded machine learning is challenging, and this is due to the large input space, the effort required for white box testing that's due to the complicated internals of the models, and the fact that these systems learn. And so emergent behaviors may only be apparent at the integration or system levels. Now, luckily, we have some ideas to deal with this. So one idea is to use combinatorial interaction testing to measure the coverage of the machine learning input space. So one idea is to use metadata, and metadata describe context in which images are collected. So examples of metadata are time of day or environment. So these are not necessarily the pixel features in the images for an image classifier, but they might say, this image was collected at nighttime, or this is an image that was collected outdoors. This is an image that was collected inside someone's home. Metadata might be a surrogate for the opaque features in the images themselves, and feature interactions might be captured by metadata interactions. So you can imagine that if we have something in the images that's due to time of day causing changes in the lighting, and maybe the inside versus outside. So maybe lighting at night outside in the dark might make an image difficult to classify versus lighting in the middle of day outside would be a very different scenario. Lighting inside, no matter night or day, because we have electric lighting, might not have the same interaction between time of day and environment. And so we might be able to capture things that are happening in the images. That low lighting scenario might be captured by the interaction between the metadata, time of day, and inside or outside. So one idea using combinatorial interaction testing is to define the input domain for features or metadata, as well as the classes. So here, classes in my example are wolves and huskies, and the environment might be snow or park or house, or however you're defining environment. And then we can think about how would we go about designing test, train, and validation splits that have coverage criteria. So we might want to say that in each split, we want to include images that have the combination husky and snow. So if everything that my training data saw lacked husky and snow combinations, and then I'm testing it on husky and snow, I might not perform well in detecting huskies in the snow. But if I make sure that each of my splits includes those interactions, then I might do better. And then further, some of these combinations just might not even exist in the data. So using combinatorial interaction testing to measuring coverage could give us an understanding of the limitation of models trained on the data. So for example, if we don't have any images of wolves and houses in our train or our test set, then we might suspect that our model might not detect wolves and houses well. So if we need to go out and deploy in an environment in which we have to, maybe it's some futuristic Google doorbell kind of machine learning model that wants to, for people living on the outskirts of society, detect if a wolf is entering your house, then perhaps if it has never been trained on wolves being seen in houses, it might not do very well at that task. So these are this is the motivation behind exploring whether or not CHIT can be useful for coverage of the input space for machine learning. So why do we think this might work? Well, CHIT addresses some of the challenges of testing machine learning. It's a black box approach, so we don't need to worry about the effort required for white box testing. It's useful for testing integrated systems. So that can be quite useful when we have emergent behaviors that are apparent only at the integration or system levels. And it's a pseudo-exhaustive strategy. And so it tends to work well for large input spaces. We don't need to worry about testing every combination of all factors. We can focus on possibly smaller sized combinations. So in some of the ongoing work, this is actually work that we presented yesterday at the International Workshop on Combinatorial Testing, IWCT, that's located at the International Conference on Software Testing, Verification and Validation workshops. We presented some metrics that we developed along with our colleagues at NIST for comparing data sets. And these metrics are intended to be used to talk about how differences between members of classes can lead to classification decisions, and also if differences between data sets are useful for predicting model performance. And these metrics can be used at 3 levels of granularity. So we can talk about the count of combinations or interactions that are present or absent. We can talk about which combinations or interactions are present or absent, so specifically wolves and houses. Or we can talk about the distribution of combinations across a data set. So we can ask the question, how often do we see wolves and houses in our data set? How often do we see huskies and snow? Are most of our images that have snow also having wolves? is it very rare for us to see huskies in snow? And then applying some of the terms that we've discussed in our earlier slides to the machine learning space, we have factors in combinatorial interaction testing, and in machine learning, these are going to be the features or metadata, depending on which we're describing, as well as the label. And again, they have to be discretized so that we have a finite set of these factor values or factor levels. A T-way interaction, also called value combination, is an assignment of values to T of the factors. And with classification, we're really interested in being able to correctly predict a label. So we have this idea of label centrism. So if I want to say, where have I seen huskies? Then I want to think about these T-way interactions, including the label, husky, and T-1 of the other features or metadata, depending on which scenario I'm referring to. So if I have two-way label-centric interactions, then I'm talking about what are the interactions, when do I see a husky along with snow? When do I see a husky and a house? So some of the metrics that we have, one is adapted from the combinatorial interaction testing literature, and this is combinatorial coverage. It is the proportion of valid T-way interactions that appear in a set. In the jump screen that I pulled up, and it showed you the coverage, and it said for T is 2, it had 100% coverage. And I think for T is 3 was about 75% coverage. That's this metric. And so if we define U to be the set of all valid examples, and U sub T is the set of valid T-way interactions, then given some data set D, that's a subset of the universe, so it's a set of valid examples. We define D sub T to be the T-way interactions that are present in that data set D. Then the combinatorial coverage of D is the size of D sub T divided by the size of U sub T, or again, it's the proportion of the T-way interactions that appear in data set D. Now this metric alone has some limitations. It's not useful for comparing two sets directly, meaning that I might have two different sets that both cover much of the universe. So they might have high combinatorial coverage, but if they are disjoint, then they don't cover much of each other. And likewise, I might have two sets that each cover very little of the universe, but if they contain exactly the same interactions, then they cover a lot of each other. They cover all of each other. And so to deal with this limitation of comparing two sets, we developed a second metric called set difference combinatorial coverage. And this measures the proportion of T-way interactions that appear in the first but not the second set. So let's assume I have two data sets, S and T, and these are both subsets of these of the universe of valid examples. Again, I define like T sub T in the same way that I did D sub T. It's the set of T-way interactions that are present in T. Then when I take the set difference, T sub T minus S sub T, I'm talking about the set of T-way interactions that are present in T, but that are not present in S. And so our set difference combinatorial coverage metric is how much of T that's not in S. So what's the size of the set difference T sub T minus S sub T divided by the size of T sub T? And we can see that the values produced by the metric represent the cases and how these two sets relate to each other. So when the value is 0, we're in cases 2 or 4. And this is where S completely covers all of T. So in case 2, S sub T and T sub T are the same. Both sets S and T have the same T-way interactions. And so we end up with a set difference combinatorial coverage of 0. In case 4, S sub T has all of T sub T's T-way interactions and then some. So S sub T is a superset of T sub T. And so the set difference of T minus S, combinatorial coverage, also is 0. When we have a value between 0 and 1, it means that S sub T covers some of T sub T, but not all. So in case 1, S sub T is a subset of T sub T, so we get a value between 0 and 1. And in case 3, neither set's a subset of the other, but there is an intersection between the two. And so some of T sub T is covered. And then in the last case, when the metric gives us a value of 1, it means that these sets are completely disjoint. So S sub T covers none of T sub T. So one application for these metrics is to talk about operating envelopes. So a machine learning model's operating envelope describes the context in which it's expected to perform correctly. So we know that machine learning testing and training is influenced by statistical learning and testing. So it relies on randomization to make the assumption that a sample is representative of the population. In other words, there's an equal chance of every example landing in each partition. But training set random selection might fail to represent the larger deployment environment. And this might be due to bad random selection. Maybe for whatever reason, when we did the random split, all of the images of huskies and snow landed in the test set, bad luck. Or it might be the case that our data pool doesn't include those interactions from the target environment, the deployment environment. So this might even be an unknown unknown. We might not know that it's not representative. So we have questions about how do we characterize the input domain on which a machine learning model is learning. And we are proposing combinatorial coverage of the training set to provide some measurement of the contexts as interactions. So if the training data lacks images of huskies in the snow, or it lacks images of wolves in houses, then the combinatorial coverage computation of the training set would show the absence of husky and snow and wolf and house interactions. And then we might conclude the model might not perform well on those classification scenarios, or at least it might lead us to go examine how the model performs in those classification scenarios. It gives us a notion that we have under coverage of those situations. Another application is transfer learning. So if we have a model that's trained in one environment and then transferred to another, possibly without retraining, this is transfer learning. Our set difference combinatorial coverage metric measures the difference or distance between the target environment and the source environment. This can help us to select images from the target environment. And we can also think about estimating the metadata from the target environment, so from the mission profile. So some possible uses of using set difference combinatorial coverage with transfer learning might be to guide source selection from a model zoo. If I have many different models I can choose from, then I can pick the one that best represents my target environment. I might be able to estimate the transferability just by having an idea of how much my source environment covers my target environment in the input space sense. I might have a way to guess how well I think the model will perform there. It might be able to be used to inform decisions to add images from the target environment to do some retraining before deployment. And it might also be useful to guide selection of images for retraining. And I'm saying a lot of might, because again, this is work in progress. So a lot of these are ideas that we're developing right now. So I'm going to walk through a quick use case of the planes and satellite imagery Kaggle data set. And so this data set has 21,000 images from Southern California and about 11,000 images from Northern California. The images either contain a plane or they do not contain a plane. And so the label on the image is plane or no plane. And the metadata that came with the data set is the location where the image was taken, south or north. And so this group tried zero-shot transfer. So when we trained on the south and then transferred to the north, there was a drop in performance shown in the my kind of top right of my screen in the chart. But when training was done on the north and then transferred to the south, there was no noticeable drop in performance. And so suspecting that there's a transfer learning problem here, when we tried to transfer from south to north, we split the data set into these two sets, using the source being the images that are collected in the south and the target as the images that are collected in the north. And then in order to use combinatorial coverage, we didn't have other metadata. So we derived 12 features from the image data itself, from the pixel data, and then bin them using 3 equal interval ranges. And so the metadata, or the features that we used, were the mean and variance values, each for red, green, blue, hue, saturation, and luminance. And so this chart to the right is just giving an idea of binned values. And so we've just assigned a value of 2 for that bin for the red mean value, for example. And so just to go back to our terminology, Two-way combinations would be like R mean and G mean, or S mean in the class column. And then two-way interactions would be R mean at value 2 and G mean at value 2 would be a two-way interaction, or S mean at value 0 and class at value 1 would be a two-way interaction. And when we computed the metrics on the planes data set, this is what we found. We used T is 2 and label-centric counting. So we're considering the class column along with one of the other features, one of the other 12 features. And so that gave us 72 interactions to consider. So in the Southern data set, 60 of the 72 interactions are covered. In the Northern data set, 67 of the 72 interactions are covered. So the North had higher coverage despite having approximately half as many images. And then when we applied the set difference combinatorial coverage, we did it in both directions. So we first asked the question, how much of the South is covered by the North? How much of the South is not covered by the North? And so what we found there is that only one of the 60 interactions present in the South is not also present in the North data set. Conversely, 8 of the 67 interactions from the North data set never appear in the South data set. So what this means is that the difference metric is correlated with the performance drop. That is, as the difference increased, performance decreased. So again, we found that the North has more interactions that are not covered by the South, and we had a problem transferring a model trained in the South to the North. So we are suspicious that what we are seeing here is that lack of coverage, under coverage of these interactions by the Southern data set is what's could possibly be driving this performance drop when we try to deploy that model trained on the Southern Plains data set to the Northern Plains data set. We can also talk about other levels of granularity. So we can list out the interactions that are absent from the Southern set, the interactions that are absent from the Northern set, or we can also list out the interactions that are in the set difference. We can say specifically, these are the interactions that we see in the North that we never see in the South. We can also look at the frequencies of interactions in the data sets, and we can even see that they have different relative frequencies. So for the same interaction, it appears with a different frequency in the two different data sets. Another idea we have is to use this for targeted retraining. So let's say we have our data sets, S and T, the Southern set and the Northern set. We compute our operating envelope. We can then use the set difference to automatically identify the interactions that are in the set difference, and then automatically identify images that contain those interactions. So I can say specifically, these are the Northern Plains images that have some interaction that's never present in the Southern Plains data set. And then we could take those images and augment the training set with those images that contain a set difference interaction. One note I have is that a better approach might be to move some of the images with interactions in the set difference, the augmented training set, but not all. Currently, we're moving all of the images. We're also exploring experiments to test zero-shot transfer on different subsets of the target to determine if the set difference images suffer from transferability challenges, whereas maybe the non-set difference images don't suffer from the same transferability challenges. Some of the preliminary results that we have on targeted retraining versus random selection suggest that subsets do not have the same performance. So let me show those quickly. So this is an experiment where we selected images in a targeted way from the North set, the target set, using different strengths of T. That's in the left column is the strength. Whether we're using label-centric or non-label-centric counting, that's not really important for this, but we have those two different ways of counting. And then the number of images is the number of images that are identified based on the size of T in the North data set that have an interaction that's not present in the South. So for example, when T is 3, we're looking at three-way interactions. When it's label-centric, we're saying it has the label column and then two of the other features involved. And we found 150 images in the North data set that have one of those interactions in it. And then we took those images and we moved them over and we augmented training. We did some retraining using those images. And then we tested the accuracy. We also randomly selected the same number of images, and this for that run, it'd be 150 randomly selected images from the northern set and added them to an augmented training set to check the accuracy of just adding more images. And what we found is that when we do targeted image selection, we have higher accuracy after this retraining than if we just randomly select the same number of images. So the chart at the bottom left, the gray line across the bottom is the 0-shot accuracy. So if we do no retraining, what is our accuracy on the target set? When we moved the images, we removed them from the target set for testing. So we're not contaminating, we don't have the same images in train and test. The blue line is the accuracy that we get from targeted retraining, from selecting images based on their interactions. And the red line is the one that we get from just randomly selecting the same number of images. We also had a question of, is this just due to more information per image? And so what we found is that we actually get more information per image by using targeted retraining than we do from this random augmentation. And we also found that the amount of information per image decreases. So in other words, we also considered adding like 879 images from the targeted set. That was using T as 5 to identify interactions. And for each image moved, the amount of the accuracy that we get for each image goes down. So in other words, we don't need to move so many images. We can get by with just retraining on a smaller subset of images. Okay. I want to give my last slide and then we can conclude. So some additional applications for these concepts are explainable classification. So looking at the interactions of features that are present in a class, not present in a non-class. Directed data collection and labeling. So if we look at the list of interactions that are in the target but not in the source, we can use that to collect and label examples for retraining to cover regions of the target environment that aren't present in the source data set. We have some ideas about using this for test set design. So let's assume we have a test set T and a training set S. When the set difference in both directions is close to 0, we suspect that this is a test environment that's representative of the train environment. But when the test minus the train set has a set difference as close to 1, we suspect that it suggests that there's many contexts that are tested that are not seen in the train. And that might be useful if we want to test generalizability to new domains, or how well does this model generalize to different test sets. I kind of mentioned the idea of using this for source selection from a model zoo. So if we have multiple models trained on different source data sets, we can look at taking the smallest distance from the target to a source to get the data set, the source data set that's most similar to the target environment. But I want to emphasize that more research is needed to explore these various different areas.